We continue here with Gauss's law. This time what we have is we have a solid sphere, except its charge density is not uniform. It varies according to this equation here. The density increases as we go out. If the volume charge density were constant, which we've seen in the past, that graph would look like that. But what we have here is we have the charge density increasing linearly. So it's essentially zero charge density at the center of this solid thing, and then it increases as we go out. What have to be the units on alpha? And this is just an arbitrary equation that the volume charge density is alpha times r. Well, volume charge density is in coulombs per cubic meter, and r is in meters. So what have to be the units on alpha? Doesn't it have to be coulombs and then meters to the fourth? So now what we're going to do is we're going to imagine this solid sphere as an infinite number of individual, very thin shells. And I've tried to represent one of those here. Radius r, thickness dr, and it has a particular charge density at that value of r. If then we were to take that shell out somehow and cut it and spread it out on a table, it would cover up this area of the table, an area equal to its surface area. And it would have a thickness, a very thin thickness, equal to d times r. So here's the area of the table that's covered, and there's the thickness, which means that the total volume of that thin shell that we're talking about is right here, 4 pi r squared times dr. Now what we want is the charge that's in that thin shell. And if you can read my chicken scratch here, rho in general is charge per volume. So if we want what's the tiny amount of charge in there, we're going to have to take rho and multiply by dV. Well, rho at some value of r, we're told is alpha times r. So this is alpha times r. At the top of the screen, we saw that dV is 4 pi r squared dr. If you multiply those out, there's an equation for the dq that results in each thin shell. So then what we're going to do is use Gauss's law. And to do that, we need to find the total amount of charge that's enclosed, all of the shells added up together. And so what we need to do is integrate this expression at the top of the screen, first from when r equals 0 to r equals little r, and then when we get beyond the outer surface of this solid, we have to integrate it up to big R, which is where the sphere ends. So that's what I've shown here. I'm integrating this dq from r equals 0 to r equals r, and we get this expression here. If we have a Gaussian sphere that's outside the solid amount of charge, then we can only integrate up to capital R because the charge ends there. So the process would be the same, except the limits would be different. And this is the amount of charge if we are talking about an R greater than big R. We're going to use those two numbers in the next part of this problem. We want to find the electric field inside and then outside the sphere. So inside the sphere, we need the amount of charge that's enclosed. And on the previous page, we just figured this out. The value of E is equal at every point. We integrate dA, and we're doing that for this Gaussian sphere right here, where little r is smaller than big R, 4 pi little r squared. And when we simplify that, that gives us an electric field inside this sphere of alpha r squared over 4 epsilon naught. When we're inside this, that's what's happening with the electric field. On the outside, the total amount of charge that's enclosed is the total amount in this sphere, which we found previously let me flip that back to be this right here. Pi alpha capital R to the fourth. Pi alpha capital R to the fourth. The electric field magnitude is equal everywhere, so we pull it outside the integral. We integrate dA, which comes out to be, look at our Gaussian sphere, it's 4 pi little r squared. When we simplify that, we get an electric field equation of alpha r to the fourth over 4 epsilon naught little r squared. Now we can maybe have a little bit of confidence in our results if we plug in little r equals big R into each equation and see what we get. And when you do that, you get this identical result. And those two results should match up at big R, because that's where those two equations should both give us the same value, and they do. All right, last page here. Epsilon naught is the permittivity of free space, and Coulomb's constant is that, and K is 1 over 4 pi epsilon naught. So what that means is K and epsilon naught have inverse units. So if K is Newton meter squared per Coulomb squared, then epsilon naught is Coulomb squared per Newton meter squared. And what does that show us about the units here? The electric field is in newtons per Coulomb. And so the question is, does our expression yield that? Alpha, we decided early on, was coulombs per meter to the fourth. R squared is going to be meter squared. And then we have epsilon naught, which has coulombs squared and Newton meters squared. And what does that yield? The meters all cancel. One of those coulombs cancels. Look at that, newtons per coulomb. That does work out. One more time. What about our other expression? Newtons per coulomb. Alpha is coulombs per meter to the fourth. R to the fourth, that's just meters to the fourth. Epsilon naught in the denominator is going to give us Coulomb squared in the denominator and Newton meter squared in the numerator, and then little r squared in the denominator gives us meter squared. What cancels? Meters all cancel. One of the coulombs cancels. Look at that. Those are dimensionally consistent. And finally, when we graph this, according to the equations that I am boxing in right now, within R, the electric field increases according to R squared. That's what we've shown. And beyond R, it decreases according to 1 over R squared.